Can you hear me in the back? It's okay? Okay, so good morning everyone. I'm Valentina Tamburello and I'm a PhD student at University of Zurich under the supervision of Lucio Meyer. My work is mainly focused on Clumps galaxy simulations, but I work also with people at the observatory in Geneva, Daniel Scherer, Miroslava de Sagesse, Antonio Cava, in order to compare my results with the observations. So my talk will be about the mass spectrum of clumps in high redshift galaxies. I know that this is the sixth talk about clumpy galaxies, so I will be very fast in introducing the topics. So the galaxies, from the observation, we know that the galaxies in the redshift range between 1 and 3 are characterized by high velocity dispersion, a low rotation to dispersion ratio, and the high gas fraction, and by clumps, some regions with size about 1 kiloparsec, and mass up to 10 to the 8, 10 to the 9 solar masses. But what they are due to interactions, to mergers. Well, yesterday we already explained very well this point. The 70% of these massive galaxies are not in the process of mergers, so the dominant interpretation is that clumps are produced by gravitational instability in the spiral arms. Until now, previous simulations have produced their clumps using weak feedback that overproduced the stellar mass relative to the abundance matching prediction. But in more recent simulation also had radiation pressure feedback. Sorry, I missed here the Gu et al. References. But anyway, they find reduced fragmentation, but still produce these giant clumps. So in my work, instead, I do a systematic study. I ran 28 isolated galaxy simulations using a gasoline tube, and in particular, I used the blast wave feedback model that was already successful in reproducing realistic disk galaxies, like in the early simulations. And I also use different subgrid physics. So, of course, I have star formation, metal cooling, radiative cooling, also metal thermal diffusion. And in some run, I also use a modern SPH formulation developed by Keller et al. In 2013. So, as I already told you, my simulations are isolated galaxies, but they are in the initial condition of my model are set up with on a base of cosmological simulation, that is the Argo simulation. So, after I selected and analyzing the feature of 26 galaxies in the Argo simulation, I put the initial condition, in particular the disk scale length, the maximum velocity, the spin parameter, and the gas fraction value in my models. And what we obtain is that we explore different galaxy mass range. In particular, the ratio M star to M halo is in agreement in our model with the abundance matching prediction by Beruzzi et al. 2013. And our models are also consistent with the observation. Recently appears this paper about Kimos sample. So this is just a table. Don't worry, I don't want to discuss in detail, but just to show you all the run that I made. So in particular, you can see in the first row that we have 11 models and 28 simulation. This is because I changed the structural parameter, and this is an opportunity that we have with the isolated galaxy simulation. So I changed the virial velocity, the concentration, and the gas fraction of our models, but also the subgrid physics involved, basically turning on or off the feedback, the metal cooling, the metal thermal diffusion. And you can see highlighted in blue the simulation that form clumps. And in the last column, there is also the duration of the clumpy phase. So now let's move to the results. Here we have some gas density maps. And here in this case, we have the same models, the same run with the same mass, the same gas fraction and concentration. But in the top panel, we turn off the feedback. And as you can see, the galaxy completely fragments. While in the bottom panels, we turn on the feedback, and you can see that it still fragments, but we form less clumps, and they disappear in 500 megayears. Then, what happened instead when we change structural parameter, like the gas fraction? Well, as Linda Tacconi yesterday said, the gas fraction is very high in the clumpy galaxies. So when we go from 0.3 to 0.5, you can see that here we have really fragmentation. And the same happens when we use lower concentration, when we start with concentration 10, and then we decrease this to fragmentation to concentration 6. Now, if we use the best parameters, so concentration 6 and gas fraction 0.5, and we explore what happens when we use different mass, galaxy mass, you can see that increasing the galaxy mass, as here from left to right, increase also the fragmentation. Even if start noticing that the clumps are at the beginning, at the formation time, have always the same mass that I will discuss in the next slide. So here is the mass function of our clumps. So we consider only gravitationally bound clumps identified with SCIT, the group finder. And we find, as you can see, the typical clump mass here, the peak is 5×10⁷ solar masses. And our clumps are really small, 200, 500 per megaparsec. And this is in agreement with the recent observation from Livermore et al. 2015, for example. So we never have kiloparsec scale clumps. Regarding the high mass tail here of the clumps, we have, of course, giant clumps, even if they are rare in respect to the other one. But the high mass tail, we check, tracking back the clump particles, and we notice that they come from clump-clump mergers, multiple, at least 4 clumps mergers. So then I want to show this next picture that will appear in a paper in preparation from our collaborators in Geneva. And here you can see that in blue you have the data from the simulation of Severino et al. 2010, and they fit, they are perfectly in agreement with the observation of the field galaxies here in yellow. But the field galaxies, you have to take into account that the best resolution that they can have at redshift larger than 1 is 500 parsec and 1 kiloparsec. Instead, when we look at the lensed galaxy here in green, like the cosmic snake or other these other work, they can resolve up to 100 parsecs in the clumps, and they found really low mass clumps. And our results, as you can see, fit best this part, while the previous result cannot fit. Otherwise, if I overplot, it was here. Well, so the initial clump mass, I don't know if I have enough time, but anyway, we decide to not use the tumor stability analysis because, as we already discussed, clumps are non-linear over density, and in this case, thick and non-axis symmetric. So we use a different estimation of fragmentation mass scale already used with success in the protostellar disk analysis. And so, we use this estimation, and if you substitute the tumor wavelength expression here, you can see that you lose completely the dependence on the surface density, so on the mass of the galaxy. And this means that if you have a more massive galaxy, you don't have more massive clumps. You just have more fragmentation, and so you can produce by mergers more massive clumps. Here, I know that I'm already late, but we can discuss about these future works during the Agora workshop. I just want to show you these CO mocks and the H alpha mocks that we want to do in the next month, and to do comparison with real data. And this is just my summary and take-home message in bold. And that's all. Thank you.
Let me ask the next speaker to come on up and get set up and take questions.
In all the cosmological simulations, it was at least partly the continued supply of new gas that led to the clump formation. In fact, it's probably part of the reason for the instability. It's also the constant minor merging. You didn't have these features in your simulations.
No.
Do you think that that could be the reason that you're not seeing clumps that are anything like the clumps that we've... Remember, every mass range from 10 to the 9 up to more than 10 to the 11 solar masses, more than 60% are clumpy in the range of redshifts 2 to 3. And they're massive clumps. In your paper, you mention that you think that the clumps aren't that massive, but that disagrees with many other observers. So what's the reason? Is it the nature of your feedback, or is it that these are isolated galaxies?
No, I think it's because the simulation are isolated galaxies, of course. We're also running some cooling LO runs now at the moment, so with the accretion of gas. But at the moment, the results are the same. If we stop at the first 300, 500 mega years, we still see small clumps. So probably also the feedback, of course, plays an important role.
Okay. Well, thanks very much.
Thank you.